Okay, well, I'm honoured to be kicking off this conference, and I'm going to share with you a paper I've just written. I hope everyone can hear me okay. Inspired by some comments from Neville Sidgwick. So basically what I'm going to do is quickly introduce Sidgwick's view. Sidgwick's article, which was basically set out in a presidential address to the Chemical Society, which is now the Royal Society of Chemistry, as the presidential address in 1936. It's very forceful, it's quite vivid. I like it, and it sort of kicked off for me a kind of working hypothesis about how to think about some of the things that go on in the development of chemistry. And so I'll look at that in the context of some case studies. And then, because this article I wrote was for a book on conceptions of progress and how they apply to particular sciences, I'll actually turn back to the debate on conceptions of progress and try and say something about that. So first onto Sidgwick. Sidgwick points out, it's quite a forceful statement here. There are two ideas about the progress of science which are widely prevalent and which appear to me to be both false and pernicious. The first is the notion that when a new discovery is made, it shows the previous conceptions on the subject to be untrue, from which unscientific people draw the very natural conclusion that if today's scientific ideas show those of yesterday to be wrong, we need not trouble about them, because they may themselves be shown to be wrong tomorrow. It is difficult to imagine any statement more opposed to the facts. The progress of knowledge does indeed correct certain details in our ideas, but the main result of every great discovery is to establish the existing doctrines on a firmer foundation and to give them a deeper meaning. So basically, I'll unpack some of those things. But let me just highlight in advance, before I look at the some of the examples, the mechanisms for cumulativity. So one straightforward way for a science to be cumulative, well, in chemistry's case, chemistry is all about thinking about the composition and structure of substances. So one way for chemistry to be cumulative is simply for progress in chemistry to constitute building up justified, true theoretical claims about the elemental composition of particular substances and or their structure at the molecular scale. So we have the growing water going from being a compound of hydrogen and oxygen, as established by Lavoisier, moving through to the 19th century to a more detailed molecular conception of its structure, and the enriching of that through physical methods in the 20th century. And another example is benzene, which through some quite kind of shaky and hypothetical atomist thinking was identified as a hexagonal molecule in the 1860s, and along came X-ray crystallography, and Kathleen Lonsdale's work established benzene to be, lo and behold, a hexagon in papers published in 1928 and 1929. So that's one way. Another way, which we've already touched on, is for chemistry to develop new experimental methods to explore the structure of particular substances at the molecular scale. So examples of that, I'll be talking about the 20th century instrumental revolution, what historians call the instrumental revolution, which is the development of physical methods and their practical and theoretical integration into chemistry. And the third way for a science to be cumulative is for it to achieve conservative extensions of its theoretical frameworks. In this case, for understanding structure and composition. I'll talk about this in a moment, but I did see Mauricio Suarez's pop up a moment ago. One example there is how the representational the content of a representation is extended by previously uninterpreted parts of the representation being interpreted, and you can track that through the inferences that are made using those representations. So that's Mauricio's applying Mauricio's inferential conception of representation, theoretical representation. So you just track what inferences are scientists using a particular representation for, and as we'll see in at least one case, the extension of structure theory in the 1870s, we can look on that extension as a conservative extension because it is simply an addition to the parts of the theory about which the chemists are using to make inferences. Okay, so moving on to the second part. This is where the fattest part of the paper. There's the historical case for cumulativity. So we start with in the obvious place, the chemical revolution that every Whig historian of chemistry will want to start. Well, they want to start there because, well, we can ask ourselves the question: was the chemical revolution a revolution? Well, in the sense that if to the extent that Thomas Kuhn was authoritative on that, obviously it was, because Lavoisier's name appears throughout the structure of scientific revolutions, and his work provides illustration of some of Kuhn's key points about scientific revolutions, that they involve the introduction of new concepts and experimental methods, and not simply, as it were, the mechanical addition to knowledge, that they involve the reinterpretation of experimental evidence and not simply the accumulation of experimental evidence. In Lavoisier's case, there were the revision of accepted compositional claims, and in some cases the reversal of them. So calces were regarded as compounds of metals and something else, rather than metals being regarded as compounds of calces and something else, namely phlogiston. And then finally, there was the introduction of a new nomenclature that was basically designed to occlude phlogiston from chemical language, to deny phlogiston a case in chemical language, so it would have no place in the description of chemical substances. Now, Ursula Klein, in a recent paper, has emphasized how much Lavoisier drew on earlier experimental work, and emphasized also the conceptual continuity of his work with that of the phlogistonists. Now, the important point here, I think, is that even if one accepts all of Klein's points, you're still left with the following facts: that Lavoisier and his collaborators developed a system of compositional claims that is still largely in use today. Although we've dropped, well, I say largely, and that the associated system of nomenclature is largely in place today. So when we think about sodium chloride, the binomial nomenclature, that comes down from Lavoisier, and also the influence of that compositional system on subsequent experimental practice, that it inspired an experimental project of analyzing chemical substances to determine their elemental composition. Obviously, if you can distinguish calces, you can distinguish what you get from them by analyzing them, and you can try and distinguish metals and so on, and you'll find more and more of them. So moving on to our second case, chemical atomism. So chemical atomism, once again, beloved of Whig historians. The problem being, of course, that so many of the individual theoretical claims that Dalton makes are, well, for instance, that water is HO rather than H2O, are foreign to us. And But Dalton does offer an atomist explanation of the laws of fixed and multiple proportions, which is pretty much the one that's accepted today. I mean, we see atoms, or we see chemical elements combine in fixed and multiple proportions because their atoms gather together in fixed and multiple proportions. Now, as Paul Needham has pointed out in multiple papers, the explanation is rather sketchy and weak because it fails to provide a mechanism for how atoms combine into molecules. So one can best regard it as a projection down of compositional claims from Lavoisier's compositional claims as compositional relationship between substances to the molecular scale. But if Dalton's explanation is a weak one, it can confer only a low degree of evidential support on chemical atomism. It's not a very good explanation because it just raises further questions. So one can see why many chemists were skeptical of it at the time, and it's difficult to say that the theory wasn't widely accepted, and it's difficult to say that it would have counted as knowledge. Now I'll return to this point because the key point is that it was a necessary stage in the development of data knowledge because it was an inspiration for both experimental and theoretical work, but it didn't itself count as knowledge. So it kind of led to progress without itself constituting knowledge, which, as we'll find out, makes it look like a counterexample to a theory of a conception of progress in which progress is simply the accumulation of knowledge. Sometimes we can't expect knowledge to grow unless we do some things which don't themselves constitute the development of knowledge. And here's a favorite quote of mine from Mendeleev, which encapsulates some of these sentiments. The law of combining weights, that's the law of fixed and multiple proportions, is formulated with great ease and is an immediate consequence of the atomic theory. Without it, it's difficult even to understand. Data for its evolution existed previously, but it was not seen until those data were interpreted by the atomic theory. Such is the property of hypotheses. They're indispensable to science. They bestow an order and simplicity which are difficultly obtainable without their aid. The whole history of science is a proof of this, and therefore one may boldly say that it is better to hold to an hypothesis which may afterwards prove untrue than to have none at all. Moving on to the periodic system, Eric, who I think I saw on the call, Eric Sherry has made a distinction between the periodic table, that is a particular way of setting out the elements to represent their relationships to each other, which may be done in a number of different ways, and the underlying system of relationships in the cells. And there's been some stability in the periodic system, except for maybe that. So minor changes would be changes to the periodic table, but more substantive changes would be changes to the periodic system itself, rather than, as it were, representations of it. Through, for instance, the addition of new groups such as the noble gases. Now, the noble gases one might think of as an addition that didn't upset the rest of the table, so one might easily regard it as a conservative extension. But what about the adoption of atomic number and / nuclear charge as a property that individuated each place in the periodic system? And according to Brad Ray in a recent paper, this demonstrates the use of a new concept of element, because prior to that, he claims, differences in atomic weight by definition entailed differences in elemental identity. But there's considerable continuity in the explanatory role of elements in theories of composition right across this period. So there's no change to that. And there was considerable semantic continuity afforded by the fact that chemists had direct laboratory, well, not direct, sometimes laborious, laboratory access to particular elements. I think the inference certainly there was some important change going on, but to the idea that we can't, as it were, identify the objects of knowledge before and after this change. I don't think that's established at all by this argument. One can just regard the early view, which Mendeleev, for instance, accepted, that atomic weight individuates the elements, which would entail this this claim of rays, as a hypothesis, a false one that was then abandoned, and the hypothesis replaced by a different identity. But we had different ways, or independent ways, of accessing the elements themselves. Finally, we get to, well, not finally, actually, we've got a few more cases yet. We get to structure theory. So theories of structure at the molecular scale were represented by an array of different kinds of diagrams and models. But the underlying structures were the same, and they were tested by what the historian of chemistry, Alan Rock, has called isomer counting. So that's where you think of a particular candidate's structure and think how many different ways there are to substitute that. So if we think about benzene, for instance, if benzene is a hexagon, then we should note there should be precisely 3 different kinds of di-substituted benzene. So if you take the 2 of the hydrogens in benzene and replace them with chlorine atoms, then you can do that in 3 ways. If they're, I'll leave you to work it out. Anyway, that's isomer counting. There should be precisely 3 di-substituted isomers of benzene. Now, those theories were themselves testable, but the representations through which they were understood and they were thought about and inferences were made were only partially interpreted. So this is a quote from Edward Franklin, once again, which I'm very fond of quoting. And what Franklin makes clear that it's only the order of the connections between the atoms which counted, and not their spatial relationships. So here's the quote: "The lines connecting the different atoms of a compound, and which might with equal propriety be drawn in any other direction, provided they connected together the same elements, serve only to show the definite disposal of the bonds. Thus, the formula for nitric acid indicates that 2 of the 3 constituent atoms of oxygen are combined with nitrogen alone, whilst the 3rd oxygen atom is combined both with nitrogen and hydrogen." So the earlier theory was silent, for instance, on whether the geometry of the earlier theory committed to carbon being tetravalent. That was Kekulé's innovation. But the earlier theory was silent, for instance, on whether the geometry of carbon, tetravalent carbon, was square planar or tetrahedral, which is basically 2 different ways to embed that connectivity into 3-dimensional space. But then the theory was extended to allow the explanation of, on the one hand, optical isomerism by Jacobus van 't Hoff, who explained optical isomerism in terms of the tetravalent carbon being tetrahedral rather than square planar. And once again, this was through isomer counting. And von Bayer's theory of strain in molecules, which, according to which some geometrical arrangements of atoms in space were preferred because there was less strain in them. In both these cases, these were stereochemical theories. They were intrinsically spatial because their explanatory power depended on their describing the arrangement of atoms in space. So what this meant was we went from a theory in which the geometrical relationships rather than the bond topology was not interpreted and no inferences were made on the basis of it, to a later theory in which the geometrical arrangements were significant and inferences were made on that basis. So insofar as this left the previous explanations unchanged. This constituted a conservative extension of the structure theory, just simply an extension of the range of things that could be explained. Moving into the 20th century, there developed a closer relationship with physics. Firstly, as we'll see through the instrumental revolution, the development of new physical methods for investigating structure, including X-ray crystallography, infrared, ultraviolet, mass and nuclear magnetic resonance spectroscopy. Now, one aspect of this was to produce an increase in the evidential support for theories of structure. So here's how Dorothy Crowfoot Hodgkin puts it, who was later get a Nobel Prize for investigating the structure of, I think it was, is it the tobacco virus? Anyway, she says at Oxford, oh, this is in her Nobel lecture actually. At Oxford, seriously studying chemistry with Robinson and Hinshelwood among my professors, I became captivated by the edifices chemists had raised through experiment and imagination. But still I had a lurking question. Would it not be better if one could really see whether molecules were as complicated as the sterols or strychnine were just as experiment suggested? So rather than having to infer the correctness of those structures, wouldn't it be great if we had a method for directly accessing, and according to her, that's what got us so interested in X-ray crystallography, because that's just what it did. So the two early developers of that, the Braggs, have described the development of X-ray crystallography as well, in terms that simply sort of an extension of seeing. So you can see that Hodgkin puts the word see there in in inverted commas. And it's a good question in the epistemology of science, exactly to what extent X-ray crystallography is a form of seeing, because it's simply a development. Because on the one hand, the actual inferential structure is quite hypothetico-deductive, so it's not that different from the earlier inferences that were made about structures. You know, how many different ways are there of arranging these atoms in space? How many different isomers can we form? On the other hand, there's a continuity argument to be had, which the Braggs ran in the little book that Hodgkin read when she was at school, in which the X-rays are simply a higher frequency version of the visible light. So it's exactly the same process, because we've got what we've done is we've multiplied by many orders of magnitude the discrimination with which we can see very small things like the structures of molecules. So looked at that way, certainly X-ray crystallography provided a new source of evidence, and one might argue that it provides a more direct source of evidence than the earlier. Certainly they were looked on in that way, notwithstanding these inverted commas for the word around the word see and observe and so on. It was regarded as a more direct method that put the earlier structural attributions on a firmer footing. So it's certainly true that there was no serious debate really about in the 1860s, there had been lots of different candidate structures which more or you know, better or worse ways fitted the reactivity of the benzene molecule. But it's a different thing entirely when Kathleen Lonsdale came along and said, well, look, here's how all these hexagons fit into the crystal structure of benzene, of solid benzene, and look, here are the as it were, the direct as it were, measurements that that give you that. So there's still this hypothetico-deductive structure, because you can advance these different candidate structures, which are then squared with the X-ray diffraction patterns. But on the other hand, some of those X-ray diffraction patterns directly represent interatomic distances. Sorry. So another aspect of the historical case for cumulativity, and there was developed an even closer theoretical relationship with physics. And that starts in the 1910s with the development of of quantum theories of the motions of molecules based on the old quantum theory, which is simply a sort of direct quantization of the motions, of the rotations and the vibrations of parts of molecules. And this is still the basis for instance, the theory of infrared spectroscopy. It's a very good basis. Then there was the development of the electronic theory of the chemical bond by G.N. Lewis in papers in 1913 and 1916, and the subsequent and consequent development of theories of mechanism, that is, the theories of changes to bonds. So this involved an extension of the interpretation of structural models to make the motions of molecules and of their parts, for instance, electrons, themselves significant. So they were, once again, they were enriched. And then finally, there was the application of quantum mechanics to explain the stability of molecules. Now, some people have thought that this, as it were, swept away Lewis's naive idea of bonds as lines between atoms. The covalent bond is a line between atoms. But it's interesting to how far that didn't happen, because the earlier structures were, as it were, constraints on the development of quantum mechanical models, because for polyatomic molecules, the intractability of the complexity and intractability of the mathematics meant that semi-empirical models had to be used, with semi-empirical models that involved special assumptions about structure that couldn't be derived from the underlying theory. In some cases, this led to the development of novel predictions, for instance, by in the context of frontier molecular orbital theory in the 1950s, for which the Nobel Prize was awarded finally in the 1980s. Yeah. The interesting thing about that final case is how you would use quantum mechanics to describe just a small part of of two very large interacting molecules, and the rest of it will just be as it were, the molecular skeleton would be assumed, but that's another matter. So it's not surprising then that there was cumulativity, there was conservation of the old structural claims, because the old structural claims were built in to the new quantum mechanical models. And then finally, I'd like to finish with an example from crystallography. So some of that, I think lots of you know about this, but it's such a great example, in particular because some of the crystallographer's work, who I'm going to talk about, Dan Shechtman, his comments, given what had happened to him, are really quite grumpy. So they're quite entertaining, and he's described his discovery as bringing about a new paradigm, and emphasized how senior members of senior scientists were undermined his work and developed how it was originally rejected for publication and was challenged by critics who offered alternative interpretations. The actual underlying interpretation is really interesting, because until the 1980s, models of crystal structure were based on the idea of a unit cell, that sort of a cell, a crystal is just regarded as being built up as from a unit cell, just repeated many times. Obviously, that builds in a tacit assumption that crystals display translational symmetry, which is the equivalent to the requirement of either twofold, threefold, fourfold, or sixfold symmetry. So fivefold symmetry or tenfold symmetry is barred. Now, in 1984, Shechtman interpreted an electron diffraction pattern as suggesting the tenfold symmetry of the underlying crystal. And as I said, his work was originally rejected for publication. It was challenged by critics, even senior ones like Linus Pauling, as offering who offered alternative interpretations. So, as I said, Shechtman describes his discovery as bringing about a new paradigm, and in one way this seems justified because there was a tacit underlying assumption of translational symmetry, that crystals displaced translational symmetry, which no one had really noticed before. It was just the model of how it was built into the model of how you thought about crystal structure being generated from a unit cell. But once it's out there in the open, you can, it's a possibility. And the interesting thing is how the structures of the crystals that Shechtman's talked about have been related to Penrose tilings, which are tilings there. So I suppose a quasi-crystal is a bit like a three-dimensional. They've been related to three-dimensional Penrose tilings, so you never quite repeat the same the units. Okay, so that's quasi-crystals. I'll finally have a few words to say about progress in chemistry and a pluralist conception of it. There are in the literature there are at least 4 conceptions of progress. In one case, classically developed by Kuhn and also Larry Loudon, that progress involves solving empirical problems. The empirical problems, as it were, are set by the theory on what counts as a solution and which problems are chosen to be worked on. There is a resistance to the idea of progress constituting anything more than this kind of internalist idea of science sets its own problems and it knows how to and how to solve them. Second idea is that progress increases, it constitutes increase in the amount of truth in theoretical representations of the world. A third one is that, developed by Alexander Bird, is that progress involves gathering knowledge about the world, developing knowledge about the world. And finally, there's the idea that it involves increased understanding of the world. So if we look thinking about the cases that we've discussed, Kuhn's functionalist account of progress is strictly compatible with cumulativity, but it hardly leads us to expect it. So it's, if theoretical developments, if cumulativity is widespread, then we might seek an explanation of that. On the other hand, it's natural to see some theoretical developments, certainly in the cases I've discussed, as responses to earlier problems and the posing of new and the development of new kinds of solutions. So, for instance, the extension of structure theory in the 1870s to account for optical isomerism was a response to a particular empirical and theoretical problem that an earlier version of the theory couldn't solve. In an even deeper way, the development of structure theory itself was a response to an earlier problem that was posed by isomerism per se. So isomerism being the idea that you can have two distinct chemical compounds which consist of the same elements in the same proportions. Well, one obvious response to that is to say that, well, these same elements must be the same amounts of the substances combined in different ways. Well, structure theory is just an account of the ways in which elements can combine together. Atomist structural theory represents this in terms of relationships between atoms. So structure theory itself is just simply a response to a particular kind of problem. The fact that you have isomerism, as it were, in pairs among the empirical phenomena of the world. That arises out of an earlier process of analyzing, an earlier experimental project of analyzing compound substances into their component elements. So Kuhn's functionalist account, it doesn't really fit well with cumulativity, but on the other hand, it solving problems is a good way to analyze certain episodes in the history of chemistry. Secondly, there's Bird's epistemic conception of progress. It's a good complement to Kuhn's because it just allows us to say that scientific progress simply is the accumulation of knowledge, and to see the value of a purely epistemic project like Lonsdale's, which is where we put on a very secure justification with a new experimental method, an earlier, more conjectural theory about the hexagonality of benzene. And some of these claims, I think that's where a lot of my thinking of this comes from. My colleague Peter Vickers has written about future-proof science, and of course, having been trained at the LSE, one would say, well, it's not really. You know, of course, it's in principle anything could be jettisoned, but really, is it really likely? I mean, how likely is it that scientists are going to decide? It's a very remote prospect that chemists are going to decide that, oh, in fact, we were wrong all along. Benzene isn't hexagonal, and water isn't, in fact, a compound of hydrogen and oxygen. I think they're pretty secure, future-proof items of knowledge. So that process of building up justification is, and our interest in it, is something that's well captured by Bird's conception. On the other hand, Bird's conception makes it harder to account for the development of speculative theories. For instance, Dalton's atomism in its early stages, where by definition the lack of evidence there's a lack of evidence of the kind that would be required for the theory or any part of it to count as knowledge. So, as we said, Dalton's theory was widely rejected, not because people thought it false, because they thought it was just too speculative, and its explanations were too pat, and there's too much in question. But yet still people worked on it, and a lot of people found it beguiling and heuristically very suggestive. And there were useful outcomes to that research. So somehow something useful came out of that knowledge, but it was that activity. But that activity itself can't really, it's very difficult to see that activity itself as the production of knowledge. So it's some other activity that led to knowledge production, but wasn't in itself knowledge production. So what that suggests to me, it's a very weak conclusion, for which I apologize, is that perhaps no single conception of progress can account for each of these examples of progress that I've been talking about. So thank you very much.
Well, thank you very much, Robin, for this very interesting talk. What I'd like for people to do is to put their hand up in using the things on the bottom, what was it called, the reactions. So you can, Olympia has a question. Oh, Olympia's clapping. Sorry, that's a clapping.
Thank you, Olympia.
We are all clapping. So does anyone have a question? Because the nice thing about using the clapping thing, the hands up thing at the bottom is that then you get pushed up to the top of the set of participants.
You have a hat on.
Someone recognized my hand. Well, thanks for a very interesting talk. I'm giving a talk on Saturday, and you've given me a whole lot of ways of thinking about how I might relate to this. But just to give you something that you might want to comment on now, my problem for next Saturday came when late in 220, I suddenly realized that I've known for many years that there are many species of animal that lay eggs, and then after a while, animals come out of those eggs and then do quite complicated things without any learning. And I wondered, did anyone know how the chemical processes inside an egg, completely enclosed in a shell, could produce all that knowledge, in addition to all the very intricate physiological structure? And basically, I found nobody had thought about the problem in the way that it's then struck me, and I've been struggling ever since then. And the ideas have been getting deeper and richer and more complicated, including having to cover many different species of for instance, reptiles, turtles, snakes, different kinds of birds and so on, and also various exceptions where, for example, the birds do not come out of their eggs and then start flying out of a nest. They have to be built up by their parents first by being fed there and so on. So there's a whole lot of special cases. But the main question is, how does the knowledge about how to behave come from chemical processes inside the egg into the newly hatched avocet that then walks down to water and starts pecking for food without having to train its neural nets? It hasn't got time to train its neural nets and doesn't need to. What makes that possible? If anyone has ideas about that, I'd love to have them to extend my own thoughts next Saturday.
So that's an interesting question about knowledge. Robin.
Yeah, no, I'm afraid I'm a blank there. I mean, I suppose one could, yeah, they're just, well, it's the behavior. It's kind of independent of the application of the norm, of the, as it were, the evaluative term knowledge, isn't it? Yeah. As well. That's the key thing, because you could just have the behaviors ingrained, programmed in. But, yeah.
Well, even that needs to be explained, because behaving requires a lot of complex control of lots of muscles and nerve fibers and all sorts of things cooperating in a systematic way. And they first have to be built up, and then the mechanisms for controlling them have to be built up, or they're built up in parallel inside the egg. And it all has to somehow be done by chemistry, because there's nothing else, unless there's some magic that nobody knows.
I was once at a conference in, it's a similar problem to this. I was once at a conference on kind of interdisciplinary scientists and philosophers, and I was responding to a chemical engineer, but one of the other papers was a cosmologist who stood up and said, well, in principle, the state of the universe at just after the Big Bang determined what I had for breakfast this morning. And I just thought, no, it didn't. There wasn't enough complexity in that state. It couldn't distinguish, the croissants from the sausages. And so I think, which is kind of underlying, there's not enough space in there. So.
Well, in some sense, the state of the universe at the beginning determined the possibility, but not necessarily the actuality. Because if the universe hadn't had that collection of possibilities, the thing you're talking about would never have been realized. So the possibility must have been there somehow, but exactly what mechanisms constitute that possibility isn't at all obvious.
Right, that's what we have. Two other people with their hands up. So Mauricio.
Yes, Thanks. I don't know if you can hear me. My connection is a bit feeble, so if you can't hear me at any point, raise a hand or let me know. Good. No, I just want to say, Robin, I really enjoyed that talk. Maybe because we've got both this LSE background that I found myself agreeing with so much in it, and in fact, in the talk that I will give on Wednesday, and I think Pedro will also probably mention it on Sunday, I think he's speaking. I've learned an awful lot of chemical chemistry from Pedro, who is in the room. We're going to be talking about Lewis structures quite a bit. And like you said today, it's really striking that they continue to be used in all kinds of different ways for inferential purposes. Even, of course, everybody knows that they are not literal descriptions of anything really going on at the quantum level. And I wanted to press you a little bit more about what sort of attitude you think we should have as philosophers towards those structures. I mean, I have my own views, but I'm sort of interested in what you think our epistemic and doxastic attitudes and methodological attitudes, which I suspect that you will be quite positive methodologically about their use. But if you could tell us a little bit more about what you think we ought to think about those uses of those representations philosophically.
Yeah, thanks. I mean, some of the things that's fascinating is where you get these little ways where you just think that's such a naive thing to do, and then they did it, and it was marvelous. It was successful. So when Ingold and Richardson were developing ways of representing mechanisms, you think, well, you've got a bond. Lewis tells you a bond, a covalent bond, is a pair of electrons. So it should be possible to convert an electron. So you've probably seen the mechanistic diagrams in chemistry, and it's just like an arrow that goes from the middle of a bond onto an atom, for instance. And it's just so simple and it's so naive. You know, you take the atom, so take that electron, that electron pair which constitute a bond. Well, if the bond breaks, the electrons have got to go somewhere, and then, so they've got to go on an atom. But because it was shared, the atoms got to require an additional charge. So it kind of moves off, and so what the bonds do, without really needing to be localized, what they actually do is they commensurate the bonds with the electrons, which is what, if they're constituted by them, that's what they should do. So you can leave aside all the kind of claims that, oh well, so this is one part. You can leave aside all the claims about whether bonds have got to be static in between atoms, because there's one thing that they do, which is they make bonds and electrons interconvertible in structure. So that when you write out a structure from the 1860s, the electrons are already in there because you've got them in between, and you can convert them into charges and so on. Another thing is that, I mean, and this isn't entirely an answer to the question, but there are various ways of partitioning the electron density distribution in molecules in ways that get at a lot of the the traditional bond structure. Unfortunately, that project itself is quite revisionary in what you get. So you get all sorts of relationships where chemists wouldn't want intuitively to put bonds. So it depends how you've got a new thing coming along, and it seems to save the old structures, not necessarily Lewis structures, but anyway, the old valence structures that preceded them. But on the other hand, it gets you more than you want. So you have these. So basically, the short answer to that is that if you apply quantum mechanics trying to recover the traditional bond structures, you can get a lot of them out, surprising amounts, but you also get some other difficult stuff. So what you're tracking is not quite the bonds in those sorts of projects. I don't know if that answers your that answers your question right there.
We have 3 other hands up, so maybe
Okay.
if Mauricio is more or less satisfied, then we'll move on. Peter Tyson.
Yeah, hi, Robin. Thank you. I really enjoyed that. And I just wanted to make a brief comment in support of your thesis that the progress of chemistry has been mostly cumulative with respect to the element definition in terms of the atomic number. So I'll be talking about this historical episode in more detail on Friday, but Planet is often credited as being one of the first to actually propose this new definition of the element. And I think what is interesting is that in the crucial paper in 1916, in which he first advanced this new definition in terms of the atomic number, Planet really emphasized the importance of historical continuity. And so he made it very clear that any new definition of the chemical element shouldn't overthrow the old definitions, but should actually complement them. And I think what's interesting is that I think for him this was some kind of epistemic motivation. I think rather than to be seen as some kind of radical who was really breaking with the past, he was much more clever to emphasize his historical continuity if he was going to convince the broader chemical community. So I wonder if this also hasn't played in some of the other episodes that you mentioned.
I think that's right, and I didn't talk about it because it was like a whole, as it were, rabbit burrow to go down. But one of the cases, one of the reasons why I think it was not merely an assertion to say that. I think one's on quite safe ground in saying that, for instance, the element names always applied to populations of atoms with the same nuclear charge. Because if you think about what a sample of silver would have constituted in the 18th century, it would have been a roughly equal mix of 2 different isotopes. I mean, you know, one might sort of say, well, that's just reinterpreting the past in terms of the present. But I mean, there's a continuous physical reality. Let's just help ourselves to that. And so, and that's why I think Planet's partly getting at is this idea that, well, populations of atoms would always have been isotopic mixtures. I mean, in some cases, you know, one can say, well, with hydrogen, it's mostly protium and there's relatively little deuterium and tritium. But with silver, it's 50-50. You can't, it's just a mix, and it doesn't matter which one. They're both, as it were, responsible for the phenomenon of silver as a metal in the 18th century. So that's why, I mean, I think it's very natural to say that. I mean, of course, on the other hand, you've got cases like gold where there's only really one stable isotope. But, you know, the thing was, if gold had more than one stable isotope, then the gold in our rings would be an isotopic mixture too. So it's that important modal fact that that makes it right to say that Mendeleev had a hypothesis that atomic weight is what individuated particular elements, and that's why I think we can say that that was a false hypothesis. It wasn't an unreasonable one to have, but it was a false one, and that we sort of and in fact the historical continuities with the how the actual reference of the names, which were to isotopic mixtures. So I'm fully agreeing with what you said, and with Panet. Thanks.
Khrushchev had a question before Eric.
Yes, I have a very short question. If a pluralistic approach to development of chemistry through history is represented in examples of a heuristic view, for instance, from Dalton, who just proposed atoms as a model, and after history, those have been somehow found by experimental methods. But there is also cumulative approach. But it is not, I ask whether it is simpler just to divide pluralistic view in two sides. One is inductive, this is cumulation, and one is deductive. This is what Dalton has done. I think such approach is known from the work of Karl Popper.
Yeah, sure. Although the I mean, I agree with that, and of course, having been trained at the London School of Economics, I as it were, tip my hat to Popper. But I suppose the problem Popper couldn't see the because of his own commitments, he couldn't see development of science as being cumulative from an epistemic point of view, which is why he developed a conception of progress. He contributed to the development of a conception of progress, which I didn't really concentrate on, which is the semantic one. So that's where you can have the truth embodied in theories is growing as theories are developed, but there's no claim that that any knowledge is primarily because Popper was opposed to the idea of epistemic justification. So each theory was as speculative as any other, but in some kind of transcendental sense, there would be the hope that the amount of truth in our theories were growing, but we would never have direct access to that fact. I mean, I think that's too pessimistic. I don't think there was any need for that, and I also think that it's difficult, I suppose. Well, it's more complicated to account for things like the gathering of evidence, which is the pure gathering of evidence, like the development of new experimental methods and applying them to, as it were, known substances to continue testing. Anyway, I don't have much to say. I think you're quite right. You could separate those out. I think that's all a pluralistic theory is. A theory of progress is doing. It's just saying, well, here's lots of different things that science can be doing. Popper, for his own part, didn't really see some of the epistemic side of. He could acknowledge problem solving, but he couldn't really acknowledge the idea of gathering knowledge. A scientific project that sets out to increase the justification of a theory to. So he couldn't acknowledge that.
Okay, Eric has a last question.
Yeah, can you hear me?
Yeah.
Thank you very much, Robin. As you know, I'm very much in agreement with the idea of the cumulative growth of knowledge. By the way, just from the previous question, Popper was very much an opponent of Kuhn. And in that respect, he was for cumulative growth of knowledge. Maybe.
Yes, that's true. Yes,
and
but not epistemic.
Right. Let me ask you to expand a little bit on one thing you mentioned when you came to talk of Lewis structures. To what extent do you think that quantum mechanics did sweep away Lewis structures? Did or did not sweep away? Well, you use the expression swept away.
Swept away, yeah. People thought it did, and people talked about it as having done so. And clearly, on the other hand, as I pointed out, it's non-accidental that you get this idea of electron pairing because it's a natural way to build it. It just gets built in to various semi-empirical methods of applying quantum mechanics to molecules. I mean, they're not quite. I mean, it's a moot question over whether those electron pairs end up between the atoms, or whether, according to Michael Weisberg, for instance, making more accurate molecular models of quantum mechanical molecular models of the electronic structure of molecules increases the electron delocalization and therefore kind of moves them away. I mean, there's a certain sense in which you can get one part of that sort of Lewis thought, which is that in Bader's quantum theory of atoms and molecules, the bond paths represent represent lines between atoms, such that if you move off that line, the electron density falls in every direction. So they're a bit like a saddle point in higher dimensions, and that in that sense you can say you've got this idea that bonding is constituted by electron density. We've got an abstraction on Lewis's idea, electron density being piled up between atoms, and it's not the same as electron pairing, but certainly that's one thing that people said in the 1920s and 30s. Was that electron delocalization is where quantum mechanics takes you, and the electron delocalization takes you away from Lewis. Well, clearly it doesn't, and it doesn't have to in this kind of slightly more abstract sense. So, yeah.
Okay, I'll be taking up some of this in my talk tomorrow.
Good.
Nice to see at least 3 people trained at the LSE here, including Mauricio, myself, and yourself. Maybe even some of the younger people were trained at the LSE, I'm not sure. Thank you. Thank you, Robin.
Thank you.
Well, we're staying very close to the time, even though we started a bit late. So thank you, Robin, for your talk. It was wonderful.